Welcome to the video on martingales and bounded variation. So today we'd like to, in this video, we'd like to start studying like regularity properties of martingales. Because the ultimate goal was, okay, we wanted to develop an integration theory with respect to martingales like the Brownian motion. And if you recall your classical analysis course, fundamental role was that you have some regular function, like continuous functions, and finite or bounded variation is a central object which appears in the classical theory of integration, like Riemann and Stieltjes integration or Lebesgue-Stieltjes integration. That will hopefully convince you in this video that you have seen it at least to some extent. Sometimes it's hidden because in a analysis course, usually you don't need to make it explicit. So, okay, let's first give you a definition so that we all know what I'm talking about. So the definition, with definition 2.12, so we need to fix some language. The first thing is I would like to introduce what a partition is. And this is a definition you might also have seen in an analysis course. So partition, in this course always denoted by capital Pi of an interval, so T, is a family of disjoint intervals. Let's call them J in the following. So J depends on S, right? This is a half open interval, so the left-hand side is not included, the right-hand side is. This is just a convention in this course, which are supposed to cover the whole interval. So you have a family of small partitions which are not overlapping, and if you take the union of all these little intervals, half open intervals, you recover the whole interval. Okay, so that's what I would like to call a partition of the interval 0 to t. Okay, and then every partition has a mesh size. So the mesh size of such a partition pi is given by, well, the mesh size just means it's the widest, the length of the widest small subpartition. So what you take the supremum over all these half open intervals, which are part of my partition pi, and then you take the maximum over it, and you measure the length of these half open intervals by taking the difference of the endpoints. Okay. Here we go. Okay. And one thing I would like to define, so dots, is what's a zero sequence is. So zero sequence is a sequence of partitions. Those mesh size goes to 0. So sequence of partitions called pi n is called zero sequence of partitions if we have the following property. So what we want to have actually some properties to make our life easier. So first thing, obviously, if we want to talk about a zero sequence, we want that something goes to 0, and this means we want that the mesh size goes to 0 if n goes to infinity. The second thing is we want that these partitions are ordered. So they're refining. So this means if you take an subinterval, so interval from the partition, the nth partition, this implies it's also every further position. No. This can be written as the union. So with this refining, so let me write it like this. So there are k's, and so and k, which are in n+1, let's say. Okay, let me put it here, n+1. And you run over k. Which are elements in the next bigger position, right? Okay, and finally, since we allow for the capital T to be infinity, we want to make the further assumption that, well, if I look at the all j which are in an interval 0 to t, we write it like this. So j such that j is in n such that j is included in the interval 0 to t is finite. Yeah, so if we take a finite interval from 0 to t, then we want that there are only finitely many elements. I mean, finally many subintervals covering. This has to hold for all t. Okay. So this is what I call a zero sequence of partition. Oh, use green again. Zero sequence of partitions. So the main point is that the mesh size goes to 0, but then I want to make my life easier, so it has to be refining, and I want to only have finitely many. So if you look at the interval of finite length, I mean, this is okay. Yeah, so this everything is well defined. Okay, so having these things at hand, we can consider now a stochastic process, right? So this is what we care about. So consider and we want that it's the right continuous, so that everything is again well defined. So let's consider right continuous stochastic process. Xt. And then we can define the variation process associated to this process X. Variation process. We label it here with taking next to bar. So we defined phi. Right. Okay. So what's the mathematical definition of this variation process? So we take xt. So we take the supremum over all partitions, which have only finitely many points in each interval, and then we sum up over all elements of the partition the increments of the path, and we intersect with the interval 0 to t, right? We won't only have to consider the partition up to time t. X. And then this is okay, and here delta, as I said, I mean, corresponds to taking the increment over the J is a half open interval. So for example, U to V intersected with T of X just is a writing for T, VT, T. Okay. So this is just looking at the increments here denoted by delta, so usual, and then we restrict each subinterval to be less than T. So we take the minimum with T. And to have everything well defined, where the supremum is taken over partitions here pi, such that here this star condition holds. Right, so otherwise the sum might be not well defined, or so we only take finitely many points. Okay. Okay. Cool. And now I claimed that this variation somehow appears in the context of Lebesgue-Stieltjes integration. So let me discuss this a bit in the next remark, so that you hopefully agree with me that indeed, I mean, this is what appears naturally in the context. This is remark 2.13. Okay. Which is Lebesgue-Stieltjes integration. Okay, so what is to do with the variation process? So let's consider an x and g. G is just a function, a deterministic function from 0 to r. So everything is one-dimensional to keep life easy. Which is first continuous. Well, this makes our life easier, and of bounded variation. What does it mean? Well, this means that the variation process we just defined here is finite. So this means if I look at here, xt, well, which was defined as before, just in terms of G. So we take the supremum of all partitions, then we sum up over all the intervals in the partition, the increments of G, right? This is now G. And this is actually equal, which is well doable to show, but not super simple. Actually, by saying, okay, I take a null sequence J n, and I let the null sequence with the n go to infinity, and take here the sum over the partition points G. And find a bounded variation means that this process is finite, right? So just a warning, I mean, this is true, you're allowed to use it, for example, from the problem sheets, but this is not trivial. This is your file sequence, a 0 sequence of partitions. Okay. So what has to do with Lebesgue-Stieltjes integration, right? And this, so if this is true, this is actually equivalent to saying at least, I mean, the bounded variation part. So, right. So, it's equivalent to saying, okay, there exists a g upwards and a g downwards. So, two functions. Non-decreasing functions, such that x is g is equal to g upwards. So this g upwards collects all the, or represents all the upwards movement of the path of the function g, and the g downwards collects all the downward movements. So right, I can represent the function g, if it's of bounded variation, in terms of a function, non-decreasing function collecting the upwards movement, and then taking the difference with respect to the downward. And okay, here you can even say I mean, they're non-negative, right? So the function can be chosen non-negative. Okay. So, okay, now you have an non-decreasing function, but this means if you have non-decreasing functions where you know how to associate a measure, so they exist measures. Let's call them mu g upwards and mu g downwards. My setting, right? So the measure of an interval for the upwards movements here, say st, it's just given by the difference of the g upwards at time t minus g down upwards at time s, right? And the same you can do for the g downwards, and you know this generates your proper measure. Okay, and s t is just an interval. So you get a measure on the interval 0 to t. Well, and if you have two measures, well, you know how to define integral. So to define the integral, let's say f, I want to integrate a function s with respect to this function g, or let's say f continuous function. We can set, right? So how do you define it? Well, this is not simple, because we know how to define integral with respect to measures. So what we do is we define the integral of s. So if you want to define the integral of f against g, we define the integral of f against the measure associated to the g upwards movement. Okay, and then we make minus the, I mean, this is the well-defined Riemann-Stieltjes integral, or Lebesgue-Stieltjes, whatever integration theory you like to have. In a simple setting, they usually agree. Right. this the same what we do here. Right, so you take minus f against downwards movement. Sorry. Okay. Here we go. So I mean, the one, at least one integral you have seen. I mean, these integrals you hopefully have seen at some point. So this means if you have a integrator G, which is of bounded variation, then it's straightforward to define an integral, which fulfills all the properties you know from others. But of course, now already in the deduction, we observe that, for example, Brownian motion, which we know now is a martingale, cannot fulfill all the standard calculus. So they need something, needs something to be going wrong. And this is basically formulated in the next lemma, which is actually a helpful lemma in a lot of context. But this lemma will tell us that we cannot hope that martingales are or have bounded variation. All right. So let x be a continuous martingale of locally finite variation. What this means, if you look at the bounded the variation process at time of x at time t, this is almost surely finite for all t in the interval 0 to t. Right. So if I'm locally, in the sense of a continuous martingale, then I know that it's almost surely constant. So the set of all omegas such that x at time t is equal to x at time 0 for all t is 1. So any continuous martingale of finite variation or bounded variation is constantly equal to the initial value. So it's a constant martingale. So, right. So this is, you're invited to prove yourself on the problem sheet. Okay. So what does it mean for a Brownian motion? For a Brownian motion, we know that it's the Brownian motion is a martingale. And we definitely know that a Brownian motion, so is not constant, right? So take a Brownian motion. Brownian motion. Yeah. All right. This Brownian motion is a martingale. And the Brownian motion is what we know the distribution at time t is given by a normal distribution. 0 to t is not constant. Not constant. So this means by lemma, what number is it? 214. If I look at the bounded variation process at time t, this has to be, to blow up for all t in the open interval 0 to t, right? And now, yes, this is what we expect. Let me make this maybe red so that you're not forgetting it, right? So how do we see this? Well, I mean, this is what we expect, and now we can like convince you by showing you some pictures, right? So this is 3-sample part of a Brownian motion. So they're certainly not constant. And now this is what you're invited on one of the programming exercises, if you're interested. Let's numerically approximate the variation process. These sample paths. Right. So if you do so, well, you can also find this in lecture notes or try it out yourself. Well, if you take 1,000, so 1,000 steps, 10,000 steps. If you describe the union interval with 10,000 small intervals, what you see is, if you look at the green one, but they look all pretty much the same, so they're close. So you only see the green color here because well, they are close to each other. So also the blue and the orange one are hidden there. Means, I mean, if you take a finite partition, it blows up faster and faster to infinity. And this is what you also see in both. So if you make the discretization finite, it immediately blows up to infinity if you take Brownian sample path. And this is what I claimed here in red. All right. Thank you for watching the video.